Okay, so in this problem, and in the upcoming ones, we're going to linearize the equation near the equilibrium solutions, and then use that to determine the stability of the solution. So there's a couple of steps. First, just as a matter of notation, this right-hand side of the differential equation is called f of x. It's a nonlinear function. We're going to linearize it around the points where f of x is equal to 0, and that is the equilibrium solutions. So step one is we need to find the equilibrium solution. You need to find the equilibrium solutions, and that's just going to be when f of x is equal to 0. So in other words, we need to solve the equation f of x is equal to 0, and for this f, this is x plus x squared is equal to 0, and by factoring out an x, this is x times x plus 1 is equal to 0, and we get two equilibrium solutions. One is going to be x of t is the constant function minus 1, and x of t is the constant function 0. So these are the two equilibrium solutions. Okay, two, at each one of these equilibrium solutions, we are going to linearize f of x around that point. In other words, that means we're going to replace f of x with its linear approximation at those points. Okay, and this, let me just write as a sort of general side work comment here. A fact from calculus that f of x is approximately equal to f of x naught plus f prime of x naught times x minus x naught. Okay, so that's what we're going to use. Now we're picking particular x naughts where that term is just equal to 0. So if f of x naught is equal to 0, then this just reads f of x is approximately equal to f prime of x naught times x minus x naught. Okay, so then the next thing that we need to do for this problem is take the derivative of f. So for us, f prime of x is equal to 1 plus 2x. Okay, and so now let's linearize at the equilibrium solution x of t is equal to 0. So that's what we're going to do now. And what it says is that near x of t equals 0, in other words, when x is close to 0, we know, so let me just say, if x is a solution, then we know x prime is always equal to x plus x squared. But if x is close to 0, then we know x prime t is equal to f of x. Okay, that's always true for any solution. But by this linearization property, we know this is approximately equal to f prime of 0 times x minus 0. Again, that's using that linearization property. Okay, so any solution, x prime is equal to f of x, no matter what. That's what it means to be a solution to the differential equation. Now we're going to use the linearization property to estimate f of x as this linear function here, or in general, affine linear function, but we call it a linear function. Okay, and so f prime of 0 is just equal to 1. If I plug in x equals 0 there, you get 1. And so this is just equal to x. Okay, so near, when x of t is close to 0, the derivative of x is approximately equal to x. That's what this is saying. If x of t is a solution and x of t is close to 0, then its derivative is approximately equal to x. And the solution to this equation is x of t, or the general solution to this equation is x of t is equal to a constant times e to the power of t. That's just the solution to the equation x prime is equal to x. Okay, so what this means, if a solution starts close to 0, it's going to be approximately equal to e to the t, but notice as t goes to infinity, as t increases, x of t is getting farther from 0. Okay, so what this means is that the solution x of t equals 0 is unstable. Okay, and again, that's because solutions that start near x of t is equal to 0 are approximately equal to some constant times e to the t, and as t gets bigger, that's going to go away from 0. Okay, now we're going to linearize. So that was the first part. So we linearized about x of t equals 0. Now we're going to linearize near the equation, or near the equilibrium solution, x of t is equal to minus 1. Okay, we're going to use the same idea. Okay, if x of t is if x is a solution to the equation, we know that x prime of t is equal to f of x, because that's what it means to be a solution to the equation. And if x of t is close to minus 1, in other words, like if it starts close to minus 1, this is approximately going to be equal to f prime of minus 1 times x minus minus 1, which turns out to be x plus 1. And if we come back up to our formula for f prime of x, if you plug in minus 1, that's just minus 1. So if x is minus 1, f prime of minus 1 is equal to minus 1. And so this is just equal to minus x minus 1. Okay, so what it says is that if x of t is a solution to the differential equation, and x of t is close to minus 1, then x prime is approximately equal to minus x minus 1. Okay, and now we're going to solve this differential equation. Okay, so if I solve x prime is equal to minus x minus 1, probably the best way to do this is integrating factors. Okay, this becomes x prime plus x is equal to minus 1. The integrating factor is e to the power of t. So the left-hand side becomes x of t e to the t prime is equal to minus e to the t. Okay, if I multiply both sides by the integrating factor, okay, if I take the antiderivative of both sides with respect to t, I get x of t e to the t equals minus e to the t plus a constant. And notice this becomes x of t is equal to ce to the minus t minus 1. Okay, if I just divide both sides by e to the t and rearrange. Okay, so what this tells me is that solutions near x of t equals minus 1. So solutions x of t near minus 1. Okay, so let me say this a little bit different. So it's not that the t is close to minus 1, it's the x is close to minus 1. So solutions x of t are approximately equal to ce to the minus t minus 1 for some constant if x of 0 is close to minus 1. Okay, so that's how we want to think about it. Solutions that start near minus 1 are approximately equal to this formula right here. And notice as t goes to infinity, ce to the minus t goes to 0. And so as t goes to infinity, as t gets bigger and bigger and bigger, the solutions are getting closer and closer to minus 1. Okay, and so this means that x of t is stable. Okay, so really what we're saying, if x of t, so let me just say this one more time for this particular example. If x of t is a solution, and x of t is close to minus 1, so it's not t being close to minus 1, it's x of t being close to minus 1, then x of t is approximately equal to some constant c times e to the minus t minus 1. Okay, and for this particular case, for this particular equilibrium solution minus 1, as t gets bigger and bigger and bigger, this approximation gets better and better and better because the approximate solutions are getting closer and closer to minus 1, which means the actual solutions are getting closer and closer to minus 1, which means the approximation is getting better. Okay, compare that to the equilibrium solution at 0. If the solutions are close to 0, if x of t is close to 0, the solution is approximately equal to c times e to the t. But as t goes to infinity, that gets farther away from 0. So the approximation gets farther away from 0, which means the approximation gets worse and worse. And we'll look at other examples, and hopefully, after you do some examples, it'll be a little more clear, if it isn't already.